Hello ATC, I'm Lucas and this long video will be about Spinfer, which is a tool to infer semantic patches from examples. Semantic patches are already used in the Linux kernel as a transformation language to help Linux kernel developers perform maintenance tasks such as API migration. Performing maintenance tasks is very common for all software projects. Usually, this task consists in removing portion of code, or removing dead code, or migrating API. But for the Linux kernel, even simple tasks can be very hard to do. Indeed, the Linux kernel is a very big code base with millions of lines of code, including a lot of code to manage drivers. And for each API, they can be used up to 1,000 times by different files across the world source tree. So even a simple API migration can end up in lots of edits for developer and can be very time consuming. Let's start with a motivating example about why performing even simple API migration can be very hard. Our example focuses on the initialization function of low-resolution timer in the Linux kernel. Originally, this initialization was performed by the function called initTimer. But in 2006, a new function setupTimer was introduced to ease the use of timer initialization. But the old function was not removed, so this migration was not mandatory. Let's look at two examples of change instances for this transformation from initTimer to setupTimer. Here you can see the usage of the old initTimer function, in which you pass a struct to this initTimer function and then you have to initialize the data fields and the function fields. With the new setupTimer API, the initialization of data and function is managed by the setupTimer function. So, to migrate from initTimer to setupTimer, you just have to replace your call from initTimer to setupTimer, add the argument for data and functions to setupTimer, and then remove the old call to initTimer and the old initialization of data and function. As you can see, this transformation is quite simple and you can understand easily what to do. And between the two examples, there is no much change except from the variable names or the order of statements. Even if this transformation is really easy to understand, it took a lot of time in the Linux kernel to get from initTimer to setupTimer. Here you can see the ratio of migrated initTimer function between 2006 and 2018. In 2006, the setupTimer function was introduced, but only a few examples were ported. The migration rise slowly until 2018, where all examples were migrated. Why is that? Because in 2018, both of these interfaces were considered insecure, and they were both replaced. But at this time, like we saw in the graph before, the API usage was somewhat inconsistent. 60% of the API on timer initialization were using the new function, setupTimer, but there were still 40% that were using the old timer interface. Since this migration is quite simple, we can wonder if it could have been done automatically, sparing some developers some precious time. Our first contribution from this paper is a classification of the difficulties of transformation. Before creating our own tool, we looked at the literature at other tools that were capable of inferring transformation from set of examples. Some of the tools, like Rephaser, Lace, AppEvolve or Meditor, are capable of doing that, but mainly for Java and Android updates. But when we tested them, we found out that it was difficult to predict whether this tool will succeed in inferring transformation from our examples. And we found out that it's because transformations can vary in difficulties, but there was no indication in the literature of any kind of difficulty metrics for transformations inference. So, as a first contribution, we created our own. We found out that changes can be organized in 5 main categories. The first one is the control flow dependencies in the transformation. Some example requires no control flow, such as replacing a simple function to another one. For some other example, it requires to have control flow dependencies with some unmodified parts, and for the most complex example, it requires to have control flow dependencies across multiple functions, making the example very hard to infer a transformation from, even from a human. Our second category is the data flow dependencies. So, some examples have little to no data flow dependencies between the modified parts, but for some other, it requires that some of the data they use come from unmodified terms in the transformation. Our third category is the number of transformation variations they can have. Some transformations have only one variation, meaning that the transformation is quite similar across all instances. But for some other, there exists some variations differences, such as the order of statement. For the most complex one, the transformation variations must be done in a certain order in order not to generate false positives. The fourth category is the number of instances that one can find in the example. So simple transformation to infer form have only one instances in their example, but most complex transformation can have interleaved transformation instances in it, making it very hard to infer a transformation from. The last category is the presence or not of unrelated change in the transformation example. For simple transformation, all the changes concern this transformation. But for most complex one, there can be some errors or unrelated changes in this transformation, or changes that are so specific to an example that they are not worth automating. If you want to have more details in these categories, there are large explanations of each of these categories and each of its subcategories in our paper. We found out that existing tool cannot handle transformation that requires to have both control flow dependencies and that have a small variation inside them. But these two constraints are very common in the Linux kernel, and they were even present in our init timer example. Consequently, this tool cannot work with our timer example and will not work with most of our kernel transformation. Moreover, the transformation rules that the tools can infer are not exposed to the developers. The developers are simply given the results of the application of the transformation rules of this tool. In this manner, the developers can check beforehand if the transformation that will be applied were correct or not, and they cannot fix them if there are small errors in them. The second contribution of our paper is our tool Spinfer. Spinfer is a tool that can learn transformation from multiple examples and that is suitable for the Linux kernel. With Spinfer, we wanted a tool that learns transformation from an example and that can both handle control flow dependencies and transformation with multiple variations, and that can also expose transformation rules to developers. Fortunately, some Linux kernel developers already use a transformation language to perform some tasks in the Linux kernel. Since 2008, Coccinelle is used to perform maintenance tasks in the Linux kernel using transformation rules that are close to classical diff rules. It was even used in our init timer example. The idea of Coccinelle is that you write a single semantic patch composed of many rules, and then you feed it to the Coccinelle engine. The Coccinelle engine will take the abstracted parts of the semantic patch and try to match these parts with concrete things in your code. If such matches are found, then it will automatically generate concrete edits for you in the form of diffs or patch. Let's look at what a semantic patch looks like. So here you have an example of a semantic patch. As you can see, it resembles strongly to a classic diff, except that it has a small header part between the two @ signs. In this part, you can declare metavariables. Here, 3 metavariables are declared and they are of type expressions. They are called E0, E1, and E2. Then there is a part where you want a change to happen. Here it's our init timer migration, with a removal of init timer and the replacement by the setup timer function. The only symbol that you may not know is the ... symbol. That means that there can exist any number of statements between the init timer removal and the data initialization removal. When we pass a semantic patch example, like the one on the left to Coccinelle, it searches automatically the code to find a suitable location for the transformation. If one or many are found, then it generates automatically diffs, like the one on the right. You can see that Coccinelle is very powerful because with its metavariables we are able to abstract many things, and so we are able to generate a lot of diffs with only one rule. Moreover, since it supports control flow dependencies with the ... syntax, we can generate changes that are only control flow dependent but are not located exactly at the same place or in contiguous lines. In our approach, we want to generate a semantic patch. So we take example of transformations as an input and then feed it to the Spinfer engine, which generates a semantic patch. Then the developer can check the semantic patch, fix it if it's wrong, and pass it to Coccinelle to generate concrete changes. So the question is how Spinfer works, or more precisely, how to get from a transformation instances to a valid semantic patch like the one on the right. I will now explain how Spinfer converts transformation instances into a valid semantic patch. So Spinfer starts with examples of transformation instances and extracts the modified statements. Here we have 2 examples of transformation instances composed of 4 modified statements each. The next step for Spinfer is to cluster together statements that are similar roles in the transformations. The clustering algorithm is detailed in our paper. Here, Spinfer created 4 clusters, one for the init timer calls, one for the setup timer calls, one for the data field initializations, and one for the function field initializations. After the clustering, Spinfer creates an abstraction, one for each cluster, that matches all members of its cluster. Here, we have 4 clusters, so Spinfer created 4 abstractions. Then, Spinfer assembled the abstraction together using the control flow information available in the examples. So, let's say that Spinfer starts by taking the init timer abstraction and create a small semantic patch rule. Then, it looks for abstraction with control flow dependencies to this one. Here, in all of our examples, the function field initialization comes after the init timer removal, so Spinfer can create these small rules composed of these 2 abstractions. Sometimes there are inconsistencies in control flow dependencies in the example. For instance, the data field initialization can come before function field initialization or after function field initialization. In this case, Spinfer simply creates more rules, one for each control flow dependencies observed in the example, and this process allows Spinfer to discover transformation variants. Here, Spinfer created 2 rules because there are 2 cases for the data fields initialization, just before function fields initialization or just after. This process of assembling abstraction using control flow information goes on until all abstractions are exhausted. The last step is to convert each abstracted expression into metavariables. Here, we have 8 abstracted expressions to convert. 1 for init timer, 3 for setup timer, 2 for the data field initialization, and 2 for the function field initialization. To convert extraction into metavariables, we need to decide which expressions are the same, so they will end up with the same metavariable's name, and which expressions are different. To do so, Spinfer looks at the term each expression represents in each example, and the two expressions will end up with the same name if and only if, for each example, the terms they represent are the same. Here, we have only 3 different expressions which will be converted to the expression metavariables E0, E1, and E2. After this step, we obtain a valid semantic patch, which is here composed of 2 rules. This semantic patch can be used by the developer with Coccinelle to generate real concrete patches. I will now talk about the evaluation we performed on Spinfer. We evaluated Spinfer by learning from real Linux kernel transformations. We constructed 2 datasets of 40 groups of transformation each. One dataset was constructed to be particularly difficult in terms of transformation challenges, as we seen earlier. The other one was selected from randomly sampled transformation in 2018. Since transformations can contain unrelated change that is not useful or not possible to automate, we evaluated the result produced by the generated semantic patch to the result produced by a semantic patch written by a human expert from the same transformation. I will now present one experiment we performed on the randomly sampled dataset. The other experiment for this dataset and the experiments for the challenging dataset can be found in our paper. So for this experiment, Spinfer was learning on the subset of the transformation and was evaluating on the complementary. So Spinfer was learning either from 10 files or half the dataset, whatever is the minimum. We evaluated 2 metrics that are commonly used in software transformation evaluation, which are precision, which is the percentage of produced change that are correct, and recall, which is the percentage of change that need to be done that were produced. In average, Spinfer obtained 87% precision and 62% recall, meaning that it covers most of the changes without doing too much false positives. For 8 groups of transformations, Spinfer generated a semantic patch that could cover the whole transformation without doing any error, meaning that the semantic patch could have been used by a Linux kernel developer directly to perform a transformation in the whole kernel. The other changes generated that were not perfect could either be fixed by developers easily or could be improved by providing more examples to Spinfer. Like I said, if you want to see more about this experiment, the details are in the paper. To sum up, Spinfer is a tool that learns semantic patches from a set of examples. Contrary to other tools, Spinfer is suitable for the Linux kernel because it can handle transformation challenges such as complex control flow dependencies or complex data flow dependencies, or transformation variations that need to be handled in a specific order in order to not produce false positives. Spinfer works by extracting modified statements from provided examples. Then, it clusterizes statements into groups that play the same role in the transformation. After the clustering took place, it abstracts each group into an abstraction that matches all of its members. Then, the abstractions are assembled in a way that respects control flow dependencies that are seen in the examples. Semantic patches produced by Spinfer can be easily checked by developer who can verify if the transformation is correct before applying it, and they can be fixed if the transformation produced either false positives or if the transformation does not cover all cases. That is all for my presentation about Spinfer, and I thank you greatly for listening to this presentation. If you have any more questions that you want to ask by email, here is my contact information.